This is question 3 from the 2007 paper, and this question is about phosphate levels in our environment. The question begins by providing some background information into the problems that can be caused by excess phosphate levels in both water supplies and blood. The introduction then moves on to explain how the concentration of phosphate ions in solution can be determined by the addition of ammonium molybdate to the solution containing the phosphate ions, which forms ammonium molybdophosphate, with each mole of ammonium molybdophosphate containing one phosphate unit. The concentration of the ammonium molybdophosphate formed can be determined by titration with sodium hydroxide using phenolphthalein as the indicator. 1 mole of ammonium molybdophosphate requires 23 moles of sodium hydroxide before the endpoint is reached. Parts A and B of the question look at the chemistry of this titration and ask you to apply some of the information that you have read. Part A of the question asks you to choose which two of a choice of 5 statements explain why so many moles of hydroxide are needed per mole of ammonium molybdophosphate. If we take each of these statements in turn, we can choose which ones we think are correct. Statement A is that sodium hydroxide is a weak alkali. We should instantly know that we can disregard this statement because this is incorrect. Sodium hydroxide is probably one of the best known examples of a strong alkali that there is. In addition, we are told that the indicator for the titration is phenolphthalein. Phenolphthalein is not a suitable indicator for titrations which involve weak alkali because the colour change takes place at a pH above the equivalence point, and so we can use this fact to support our decision that statement A is incorrect and can be disregarded. Statement B is that ammonium molybdophosphate has a very high molecular mass. Although we do not know the formula of the compound, we can imagine that this is probably true. However, the mass of the compound would not help to explain why so many moles of alkali are needed, as with titrations it is the number of moles of the compounds involved which is important, and so we can disregard statement B. Statement C says that the molybdenum containing species is acidic. This must be true for neutralization to be possible by the addition of alkali. Although it doesn't really help us to explain why so many moles of hydroxide are needed, it does help us to explain why hydroxide is needed, and so we can tick this as one of our good statements. Statement C says that phosphate ions are acidic. By definition, a Bronsted-Lowry acid is a substance that can donate a proton. If we write out the formula of a phosphate ion, PO4 3-, it clearly has no protons to donate, and so we can rule out this statement purely on the basis that it is incorrect. Finally then, statement E is that the molybdophosphate ion contains many molybdenums. Although we do not fully know the structure of the ammonium molybdophosphate complex, since the phosphate is not acidic, then it must be the ammonium molybdo bit which is. Ammonium ions are weakly acidic, but since 1 mole of hydroxide reacts with just 1 mole of acid, and we know that each mole of ammonium molybdophosphate requires 23 moles of sodium hydroxide for neutralization, then we can tell that the ammonium molybdo bit must contain many moles of acid, and so we can predict that this final statement, that the molybdophosphate ion contains many molybdenums, is true and helps us to explain why so many moles of hydroxide are needed per mole of ammonium molybdophosphate. And so in answer to question A, we can predict that the 2 statements which help us to explain our facts there are statement C and statement E. Part B of the question then asks you to use the information that has been given about the titrations to calculate the concentration of phosphate in 10 centimeters cubed of treated blood serum, given that the blood serum was reacted with an excess of ammonium molybdate the precipitated ammonium molybdophosphate required 17.25 centimeters cubed of a 0.01 mole per decimeter cubed solution of sodium hydroxide. The first thing we need to do with this information is to calculate the number of moles of sodium hydroxide required for the neutralization. We can do this by applying the equation that the number of moles is equal to the concentration, which in this case is 0.0100 moles per decimeters cubed, by the volume given in decimeters cubed, so that's 17.25 centimeters cubed divided by 1,000. And if we do this calculation, we calculate that the number of moles of hydroxide needed for the neutralization is 1.725 times 10 to the minus 4. Now, from the equation for the titration which is taking place, we know that 1 mole of ammonium molybdophosphate requires 23 moles of sodium hydroxide to reach the endpoint. And so, knowing this fact, we can calculate that the number of moles of ammonium molybdophosphate formed in the reaction must be equal to the number of moles of sodium hydroxide, the 1.725 times 10 to the minus 4, divided by 23, which gives us a number of moles of ammonium molybdophosphate formed in the reaction as 7.5 times 10 to the minus 6. Now, in the introduction, we were told that each mole of ammonium molybdophosphate contains 1 phosphate unit. So if we know that the number of moles of ammonium molybdophosphate formed is 7.5 times 10 to the minus 6, we must also know then that the number of moles of phosphate must be equal to that 7.5 times 10 to the minus 6. Finally then, if we know that there are 7.5 times 10 to the minus 6 moles of phosphate present in 10 centimeters cubed of the blood serum, we can calculate that the concentration of phosphate in the blood serum is the number of moles, 7.5 times 10 to the minus 6, divided by the volume of 10 centimeters cubed, but given in decimeters cubed, which gives us a final concentration of phosphate ions of 7.5 times 10 to the minus 4 moles per decimeter cubed. Part C of the question introduces you to the fact that the degree to which a phosphate ion is protonated in aqueous solution depends upon the pH of the solution. The question provides the acid dissociation constants for each of the 3 dissociation steps of phosphoric acid and asks you to calculate which form of phosphate is prevalent in blood serum which has a pH of 7.4. If we start off by looking at the dissociation of a weak acid, HA, we can say that the acid dissociation constant is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA. In order to determine which form of phosphate is prevalent in blood serum, we need to determine the ratio of A minus to HA, or the deprotonated to protonated form, for each of the dissociation steps. Since we know that the Ka is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA, we can rearrange this to give a value for the ratio of A minus to the concentration of HA as being equal to the acid dissociation constant divided by the concentration of H plus. Since pH is equal to minus log of the concentration of H plus, and we know the pH of the solution to be 7.4, we can calculate the concentration of H plus to be equal to 10 to the power of minus 7.4, which is equal to 3.98 times 10 to the minus 8 moles per decimeter cubed. With this value to hand then, we can now run through each of the dissociation steps and calculate the ratio of A- to HA by dividing the acid dissociation constant by the concentration of H+. So looking at the first dissociation, we know that the Ka1 is equal to 7.9 times 10 to the minus 3, and so we can determine that the ratio of the deprotonated to the protonated form is equal to 198,439. So what does this actually mean? This tells us that this equilibrium lies a long way to the right, with the concentration of H2PO4- being much higher than the concentration of H3PO4. So if we do this for each of the other two dissociation steps, for the second acid dissociation, Ka2 is equal to 6.20 times 10 to the minus 8. And so in this case, the ratio is much smaller, with the value for the concentration of the deprotonated divided by the concentration of the protonated form being equal to 1.55. So in this case, the equilibrium still lies over to the right, but it's much more balanced, but the concentration of HPO4- is now the higher concentration. Finally then, looking at the last dissociation, Ka3 is given as 4.4 times 10 to the minus 13. If we do this calculation then, we find that the ratio of the deprotonated to the protonated form is equal to 1.11 times 10 to the minus 5. In this case, since the ratio is smaller than 1, we know that this equilibrium lies to the left-hand side and the HPO4- dominates. So having calculated each of these ratios, what does this mean for the prevalent form of phosphate at pH 7.4? The first equilibrium tells us that H2PO4- is the preferable form. However, this then feeds into the second dissociation and dissociates to HPO4- However, the HPO4- formed in the second acid dissociation doesn't dissociate any further because the third dissociation lies to the left-hand side. So in answer to the question, which form of phosphate is prevalent at pH 7.4, we can say that the answer is HPO4- The final part of the question moves on to look at some possible treatments for high levels of phosphate ions either in the blood, which is known as hyperphosphatemia, or in pond water. In both cases, the excess phosphate ions are removed as precipitates. In blood, the precipitate formed is lanthanum phosphate, which is formed by the reaction of lanthanum carbonate, which is marketed as the drug phosphorol, with the excess phosphate ions in the blood, or in pond water, the precipitate is aluminium phosphate, which is formed by the addition of aluminium sulfate. Part D of the question asks you to write an equation for the reaction between the phosphorol, the lanthanum carbonate, and the hydrochloric acid, which is present in the stomach. The first thing to do with this question is to work out the correct formula for lanthanum carbonate. Since in the introduction you are told that lanthanum phosphate has a formula of LaPO4, and knowing that a phosphate ion has a 3- charge, you can work out that the charge on a lanthanum ion is 3+. Knowing then that the formula of carbonate ion is CO3 2-, and knowing that in an ionic compound the overall charge on the compound has to be equal to 0, we can work out that the lanthanum and carbonate ions must combine in lanthanum carbonate in a ratio of 2:3. Now when a carbonate reacts with an acid, the products of the reaction are a salt, carbon dioxide and water, and so we can apply that same basic equation to the reaction of lanthanum carbonate giving the products of the reaction as the salt, lanthanum chloride, plus carbon dioxide, plus water. All that remains now is to balance the equation. So starting off by looking at the lanthanum ions, each equivalent of lanthanum carbonate contains 2 lanthanum ions, so we know that we must form 2 equivalents of lanthanum chloride. Each of these equivalents of lanthanum chloride contains 3 chloride ions, so we know that the reaction must involve 6 equivalents of hydrochloric acid. Looking at the carbonate ions, each equivalent of lanthanum carbonate contains 3 carbonate ions, so we know that we must produce 3 equivalents of carbon dioxide. And then finally, balancing the hydrogen atoms, we've got 6 hydrogen chlorides, and so we know that we must produce 3 equivalents of water. The final part of the question then moves on to look at the solubility of the phosphate salts formed in the precipitation reaction. The question introduces something called the solubility product of a salt, which is given the symbol KSP, and tells us that it is equal to the product of the concentrations of each of the ions in the salt at the point of saturation. So for lanthanum phosphate, the precipitate formed by the reaction of lanthanum carbonate with any excess phosphate ions, we know that the solubility product, KSP, is equal to the concentration of lanthanum ions at saturation multiplied by the concentration of phosphate ions at saturation. Part E of the question asks you to use the values given in the questions for the KSP to calculate the concentration of a saturated solution of lanthanum phosphate. Since the formula for lanthanum phosphate is LaPO4, then each mole of lanthanum phosphate contains an equal number of lanthanum and phosphate ions. Therefore, at saturation, we can say that the concentration of lanthanum ions will be equal to the concentration of phosphate ions. So knowing this, we can say that the value for KSP of lanthanum phosphate, which is given in the question as 7.08 times 10 to the minus 27, will be equal to either the concentration of the lanthanum ions at saturation squared, or it will also be equal to the concentration of phosphate ions at saturation squared. So working out this equation, so square rooting the KSP value of 7.08 times 10 to the minus 27, we can calculate that the concentration of either the lanthanum ions or the phosphate ions at saturation is equal to 8.41 times 10 to the minus 14 moles per decimeters cubed. Since each mole of lanthanum phosphate contains 1 mole of each ion, then the concentration of each ion at saturation is also equal to the concentration of the salt at saturation, and hence we can give the final answer for the concentration of lanthanum phosphate at saturation as 8.41 times 10 to the minus 14 moles per decimeters cubed. Finally, in part F of the question, you are asked if an equimolar solution of aluminium and lanthanum ions is added slowly to a solution of phosphate ions, which of the 2 possible phosphates, either aluminium phosphate or lanthanum phosphate, would precipitate first? Now, a salt precipitates out when its concentration goes above the concentration of the saturated solution. The solution can't hold any more salt. So from the calculations in part E, we know that lanthanum phosphate would precipitate out at a concentration of 8.41 times 10 to the minus 14 moles per decimeters cubed. If we do an identical calculation to that we performed in part E, but this time for aluminium phosphate, since it too contains an equal number of aluminium and phosphate ions, then we can say that the concentration of aluminium ions at saturation will be equal to the concentration of phosphate ions at saturation, which will be equal to the concentration of aluminium phosphate at saturation, which will be equal to the square root of KSP for aluminium phosphate. And so if we do this calculation, we can calculate that the concentration of aluminium phosphate at saturation will be equal to the square root of 9.84 times 10 to the minus 21, which is 9.91 times 10 to the minus 11 moles per decimeters cubed. Finally then, from our calculations, we can see that the concentration of lanthanum phosphate at saturation is lower than the concentration of aluminium phosphate at saturation, and so the phosphate which would precipitate out first would be lanthanum phosphate.